Hello, let's take a look at the section 3.2 notes. We're going to be talking about Rawls' theorem and mean value theorem. So in section 3.1, we talked about the extreme value theorem, and hopefully you remember that the extreme value theorem said that if f is continuous on a closed interval and differentiable on the open interval, then there existed some c in that interval, or actually they guaranteed that there was a maximum and a minimum in that interval, an extrema in that interval. All right, and so what we said was, hey, that's really cool, but sometimes what we found was that if the function was, let's say, always increasing or always decreasing, that those endpoints occurred at the max and the min would occur at the endpoints, that it didn't occur in the interval, but at those two endpoints there. So there was a French mathematician whose last name was Rawls, and he wanted to ask the question, how can I guarantee that there will be a max or a min, an extrema, somewhere in the interval, not at the endpoints of the interval, but somewhere in between A and B, whatever that is. And so he said, okay, here's what I need to do to make that happen. First, f is continuous on a closed interval, same. It's differentiable on the open interval, same. But he has to put this requirement in here that f of A and f of B, in other words, the values at the endpoints, have to be equal to each other. Then there is at least one number c in that open interval such that the derivative is 0. So again, think about if we say that we've got some function, here again is my a and my b, so that f of a equals f of b, then I can do things like this in there, and it's going to guarantee that I have an extrema, two extrema, one max, one min, inside that interval right there. Actually, I don't think it has to be two. I think it just has to have at least one. No, I think it has to have two. So what that's saying is that, let's see, if these are the same, then, and we connect them like that. Remember, that was called the secant line. That the secant line, the line that connects those two endpoints, that there will be there will be some other point. Yeah, it doesn't have to be both, and it doesn't have to be both. It just has to have at least one max or min in that interval. And so what it's saying is that there is some other point, maybe more than one, where the derivative will also be 0. All right. So it's not guaranteeing both a max and a min in there. It's guaranteeing at least one of them in that interval. All right, so again, the slope of the secant line right there is going to be 0 because f of a and f of b are equal to each other. But it's guaranteeing that at some point in there, there will also be another point in there who's not secant anymore, because we're just talking about instantaneous rate of change here, or the instantaneous slope, will also have a slope of 0 right there. And again, in this diagram, there's 2, but it doesn't have to be 2. Okay, so example 1 says, find the two intercepts of the function f of x equals x squared minus 3x plus 2 and show that the derivative is 0 at some point between the two x-intercepts. Okay, so again, normally we would be given a closed interval, as we were, when we did the extreme value theorem. But here they're not giving us one, but again, what they're saying is find these two intercepts, because we know at the intercepts, at the x-intercepts, that they will be the same value. All right, so it's asking us to find those two. So let's do that first. So we want to know when x squared minus 3x plus 2 is equal to 0. All right, I'm going to factor that, and I get x plus 2, x plus 1. And that tells me that my zeros, right, where the x-intercepts are at x equals -2 and x equals -1. Sorry, I totally just messed that up. This should be minus, that makes this plus and plus. Okay, so if we were, so then that gives us our interval right here. It's 1 to 2, because again, we know that at 1, the function is 0, because it's an x-intercept, and we know at 2, the function is 0, because it's the other x-intercept. And so what we have is that this is our f of 1 equals f of 2. All right, so that requirement that Rawls' theorem says to be continuous, well, we'll go through those in just a second, but we have to have a closed interval, and so that is the closed interval that Rawls' theorem is talking about. Okay, so let's just make sure that everything applies here. So it has to be continuous on a closed interval. So again, there's the continuity. All right, so is this function continuous on our closed interval of 1, 2? Well, yes, because every polynomial is continuous everywhere. So specifically, it's continuous on that. So yes. Is it differentiable on the open interval? And again, polynomials are always continuous and differentiable everywhere. So yes, it's continuous. Sorry, I didn't mean to put a, b. I meant to put 1, 2. It is differentiable there, yes. And then is f of 1 equal to f of 2? Yes, we just found that because they are the x-intercepts, they are equal to each other and they're equal to 0. All right, so then that means that we can apply Rawls' theorem. So what does Rawls' theorem say? Well, it says if we have all these conditions met, right? It's continuous on the closed interval, differentiable on the open interval, and f of a equals f of b, then this is what we get to conclude. There's at least one number c in that open interval, ab, such that the derivative is equal to 0. All right, so we need to find the derivative, because it's asking us when the derivative is equal to 0. So f prime of x is going to be 2x minus 3. And we want that to be 0. All right, so I'm going to solve for that, and I end up getting x equals 3/2. All right, but we need to give the ordered pair. So we would plug that back in here. So I've got 3/2 squared minus 3 times 3/2 plus 2. This is going to give us 9/4 minus 9/2 plus 2. Let me change them so they all have the same denominator. So 9/4 minus 18/4 plus, if we change that to 4, we get 8/4. That's going to give us negative 9/4 plus 8/4 is going to give us negative 1/4. All right, so we could say the ordered pair, let's say, at the point 3/2, negative 1/4, f has a horizontal tangent line. Or you could also say at the point 3/2, negative 1/4, f prime is equal to 0. Okay, now that shouldn't surprise us too much. This is a quadratic, so it's going to be a parabola. All right, so here are our intercepts at 1 and 2. All right, we also know its its y-intercept is up here at 2. It's going to open up because the coefficient of x squared is positive, so it's going to look something like this. But better, probably. Let's see. At 3, it's going to be up here at 1. Okay, and so we can see that the point 3/2 right here falls right between 1 and 2, and then that would be that spot where it's the tangent line is horizontal, or the slope is 0 there. The slope of the tangent line is 0. Okay, let's take a look at example 2. So example 2 says that we have this function f of x equals x to the 4th minus 2x squared, and we're supposed to find all values of c in the interval negative 2 to 2 such that f prime of c is equal to 0. All right, so let's just check to see that we have these things. So let f be a continuous function. Yes. Again, it's a polynomial. They're continuous everywhere. And we're given this open interval, which might seem alarming, but again, remember, the function is continuous everywhere, so it doesn't really matter whether they've given us open -2 to 2 or closed -2 to 2, because it does apply. As long as those the spots where the derivative is equal to 0 don't occur there, then no harm done. Okay, so then let's see what we've got. So is f continuous? Again, I'm asking you to do this because there will be times where it's going to say verify that you can use Rawls' theorem, or there's going to be times where it doesn't, it just doesn't apply. So we just have to check to make sure. All right, so is f continuous? Yes, it's a polynomial. All polynomials are continuous everywhere. Is f differentiable? Yes, it is. Again, polynomials are differentiable everywhere. So then it comes to the question is f of -2 equal to f of +2? So let's check that. So we've got, for -2, we've got -2 to the 4th power minus 2 times -2 to the 2nd power. That's giving us 16 minus 2 times 4, or 8, which is going to give us 8. And then we notice that this is an even function. If we plug in 2, we're going to get the same thing. So 2 to the 4th minus 2 times 2 squared, that's 16, and again minus 8, and we get 8. So yes, this is correct. Okay, so then let's go ahead and find those values of c that are guaranteed by Rawls' theorem. Right? So again, we need to find that value of c where the derivative is equal to 0. So first we take the derivative. That's 4x cubed minus 4x. And we want that to be equal to 0. All right, I'm going to factor out the 4x, so we end up with x squared minus 1 equals 0. And then I'm going to factor even more. I've got a difference of squares here, so x plus 1 times x minus 1 equals 0. This is going to give us x equals 0. This is going to give us x equals -1, and this is going to give us x equals 1. All right, so it's saying that at those 3 spots, the derivative is equal to 0, and hence they're either going to be maximum or minimum, but there will be an extrema. Okay, so let's find out what the y-coordinate is that goes along with this. So when x is 0, we plug it back into that, and we end up with 0. And then we do the same thing for -1. And we plug that in, and we get 1 minus 2 is -1. And we do it for 1, and we plug that in, and we also get 1. All right, so those are the 3 points that are guaranteed by Rawls' theorem. Actually, not all 3 are guaranteed by Rawls' theorem, but just at least 1. Okay, let's take a look at what this looks like. So at 0, 0, we've got a point there. At -1, we're at -1. At 1, we're, oops, sorry, this should be -1. We've got -1. And we've talked about end behavior. You talked about that last year. And we know if the highest exponent is even, then it's going to have a pattern like this, where its end behavior is it goes off to either positive infinity or negative infinity. Both of them, both ends do. And so here, since this is positive, it's like this, as opposed to both of them going down like that. So positive. And so we can say, oh, it must look something like this. Let me scooch that over a little bit. It's going to come up and go down and then come back up again, like that. Right, and so here, these two would be our, in fact, in this case, absolute min, but we could just say minimums, and this would be a relative max right here. All right, so these are the values C, and these are the points at which they occur. Okay, so then let's take a look at the mean value theorem. So the mean value theorem says something very similar to Rawls' theorem. If f is continuous on the closed interval a, b, and it's differentiable in the open interval AB, then there exists a number C in AB such that f prime of C is equal to f of B minus f of A over B minus A. You might look at that and say, what the heck is going on? All right, so we can think of this in two different ways. One is just from, what does it look like? All right, so let's say I have some point. So again, notice here that it's not requiring that f of A equals f of B like it did for Rawls' theorem. So f of A, so again, let's say this is A and this is B, f of A might be here and f of B might be up here. All right, so we still draw the secant line right there, but what we notice is it's no longer horizontal like it was in mean value theorem. I'm sorry, in Rawls' theorem, it's no longer horizontal. Okay, and so what's going on is we've got some function, I don't know what it looks like, but maybe it's like this. All right, so from a very visual perspective, what it's saying is that the slope of the tangent line here, the slope of the secant line here will be the same at some other point in there. Again, this is the formula for slope. All right, so it's saying f of B minus f of A over B minus A. This is the slope of the secant line. All right, that's the line that crosses through our two endpoints right there. So it's saying the slope of the secant line has to be equal to the slope of the tangent line at some point C. So I would guess maybe we're talking about right here, that there is some point C where when I find the tangent line, it has the same slope as the slope of the secant line. Right? Now, maybe that's going to occur more than one time in that interval. It looks to me like this happens again down here, just for my picture. Maybe it's only going to happen once, maybe it'll happen more than one time. But it's saying that the slope of the secant has to equal the slope of the tangent. Right? And again, that's different from when we did Rawls' theorem here, because we said actually the slope of the secant equals the slope of the tangent. But that slope is 0 because f of A equals f of B. We're not requiring that anymore, and so we're going to have to figure out what that slope of the secant line is, because we won't know it right away. So again, you might look at this and think, okay, there's less requirements at the beginning. F is continuous on the closed interval and differentiable on the open interval. And that's one less thing than Rawls' theorem requires. But there's this part at the end that actually requires you to do maybe a little bit more than what Rawls' theorem said to do, right? So this is the part where I feel like people get kind of a little bit stuck because they're like, what the heck is this saying? And also it just means a little bit more work. But let me also say this from a just kind of a conceptual idea here. Again, this is the slope of the secant line, but we can also say this is the average rate of change. On AB. Right? So what it's saying is that the average rate of change on AB over that interval is somewhere equal to the instantaneous rate of change. Sorry, I don't have enough room there. Okay, so we can say the slope of the secant line equals the slope of the tangent line at some point in that interval, but it's also saying that the average rate of change on that interval has to equal the instantaneous rate of change at some point in the interval. Right? And again, this is going to be the part where you're like, okay, I know I've got to check for continuity, I've got to check for differentiability, I've got to find the slope, I've got to find the derivative, but at some point we have to know what to set it equal to. In Rawls' theorem it was equal to 0, but in mean value theorem we have to find that value. Okay, so let's take a look at example 3 here. It's saying we've got some function f of x, which is equal to 5 minus 4 over x, and we're supposed to find all values of c in the open interval 1 to 4. such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Okay, so first of all, let's note that this is an open interval, right? And you might say, oh my gosh, we probably can't do it. In fact, we go over and look at this and we say, oh gosh, this is not actually continuous. This has a discontinuity, in fact, a vertical asymptote at x equals 0. So we think, okay, that might just totally mess us up here. We might not even be able to use mean value theorem. But again, that spot where we've got that vertical asymptote is at 0, and that is not in our interval right here. In fact, it's a whole 1 unit away from it. So we could say that on 1 to 4 closed, it is continuous, right? And again, it is differentiable because it's just only not differentiable at the spot where that vertical asymptote is. Let me just show you what that looks like. It's got a vertical asymptote at 0. And if we just plug some things in here, at 1, which is the beginning of our interval, 1, we plug 1 in here, we get 4 over 1, which is 4, 5 minus 4 is 1. So at 1, it equals 1. And then 2, 3, 4, right here is our other endpoint. And if I put 4 in here, 4 over 4 is 1, and 5 minus 1 is 4. So 2, 3, 4, so we're somewhere up about here. And we also know that this is an asymptote right here, so it's got to look something like this. Right? And so we can say we're just limiting our attention to this space, this part of the curve. Okay, so find all values of c in the open interval such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Again, remember, this is the slope of the secant line. It's just y2 minus y1 over x2 minus x1. So this is asking us to find the slope here of this. And then it's saying that at some point c in this interval that goes from 1 to 4, there is a point where the slope, the instantaneous rate of change, the slope of the tangent line, will match that slope. Okay, so let's figure out what this is. I usually like to try to get that done right away because I feel like when I get to this point, if I haven't found it yet, then I sometimes panic and think, what did I forget to do? So this is it. So f of 4, we just found that out, was, it's 4, minus f of 1, which is 1, over 4 minus 1. Right, and we end up with 3 over 3, which is 1. Right, so it's saying the slope here is 1. That makes sense because we're just rising 1, running 1, and so forth until we get from 1, 1 to 4, 4. So the slope is 1. And so it's saying at some point c in here, the derivative is also going to equal 1. All right, so now let's find the derivative. So f prime of x, I'm just first going to rewrite this as 5 minus 4x to the negative 1. So when I take the derivative, the 5 is just going to go away because it's a constant. And so then I'm going to end up with positive 4x to the negative 2. All right, I'm going to rewrite this as 4 over x squared. And what this tells me is that this instantaneous rate of change, or the derivative, at some point is equal to the average rate of change, or the slope of the secant. Okay, so I'm going to take and I'm going to set that equal to 1. So instantaneous has to equal average at some point in that interval. All right, so let's solve for that. I'm going to cross multiply and I'm going to get 4 equals x squared. And then we're going to say, oh, that means that x equals plus or minus 2. Now I forgot to do this when we did this over here, is to just check to make sure that those points that we get are within the interval. All right, so here 3/2 is definitely in that interval 1 to 2, right? It's greater than 1, less than 2. And then here 0, -1, and +1 are all within that interval -2 to 2. The reason I'm saying that, I'm pointing it out, is because sometimes we end up with a place where the slope of the tangent line is 0, or in mean value theorem, the case would be where it's equal to the average rate of change over that interval. But it's not within the interval. So let's say I was doing like this, and I ended up with, here's -2, here's +2. I might end up with something where I have the slope is 0 here, but it's not within the interval. All right, so just double check to make sure that that is a spot where the derivative is, where the spot where the derivative is 0 is within that interval. So 0, -1, +1 are all in there. And again, we need to check that for this as well. And again, the reason I'm bringing this up is because, in fact, +2 is within that interval, but -2 is not. All right, so we only want x equals +2. All right, and so that's saying that at the point 2, comma, let's find out what that y value is. So if we put 2 in here, 4 over 2 is 2, 5 minus 2 is 3. So at the point 2, 3, f prime of 2 is equal to f of 4 minus f of 1 over 4 minus 1, or you could say at f prime of 2, sorry, at the point 2, 3, the slope, or the instantaneous rate of change, I'm just going to write ROC, rate of change, equals the average rate of change. On the interval 1 to 4. You don't have to write both, you can just pick one of them, but this is the point that we're looking for, 2, 3. Okay, let's take a look at the next example. Okay, so in example 4, this is an application of the mean value theorem. So you probably don't remember a time where there was not E-ZPass, but when E-ZPass was being suggested, there were a lot of people that were really concerned that it was going to be misused and not just used to quickly collect the toll on the turnpike. And this is the reason they were concerned. So 2 stationary patrol cars are equipped with radar, and they're 5 miles apart on a highway, as shown in figure 3.14 on page 175. I'll draw that in just a second. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is checked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some point during the 4 minutes. So people were concerned that they were going to apply the mean value theorem to find out when you got on at, let's say, Fort Washington and you got off at King of Prussia, that your speed exceeded the speed limit. That hasn't happened, but that was definitely a concern. But again, that would have been done using mean value theorem. So let's draw what we've got here. So this is the turnpike, and we have 2 patrol cars that are stationed on there. So I'm going to draw the first one right here and the second one right here. And so this truck is traveling this direction, right? And so it tells us that they're stationed 5 minutes apart. Not minutes, miles, right? So we'll say that this distance right here is 5 miles. All right, and the truck is coming along, and it's clocked at 55 miles per hour when it gets here. All right, so this is patrol car 1, and this is patrol car 2, and it's 55 miles per hour here. And then when it gets to this one, it's 50 miles per hour. So it looks like it's slowed down, actually, but we're going to find out that that is not the case. All right, so 4 minutes later, so again, it's starting here, 4 minutes later, this is what happens where this patrol car clocks it. All right, and it's checked at 50 miles per hour. Prove that it must have exceeded the speed limit of 55 miles an hour at some point during those 4 minutes. All right, so again, this is 5 miles, but it's also 4 minutes. Okay, so let's first talk about why we would even consider using mean value theorem. So first of all, there has to be some sort of position function that tells us where the truck is at any point in time. And so that function, again, think about the continuity part, is that we don't draw the position of the truck and then just suddenly like skip over parts, like that I would have to pick up my pencil and draw its path or its position. I don't have that, all right? The vehicle just is moving in a way that we would consider continuous, right? As you're driving, it hits every value between there. It doesn't skip any. We don't have anything weird happening. So when we're driving, we assume our position is a continuous function. Okay, so then I'm going to have my position function be called s of t. I have no idea what that is, right? I don't know how the truck is speeding up or slowing down, but it's okay. It doesn't matter. I just know that it does have some position function, and that's going to play the role of our function f, all right? Although we don't know what it is, but we can say that because this is a continuous function and it is differentiable, again, as we slow down or speed up, we're not going to do anything weird like I'm slowing down and then instantly I'm speeding up. There would have to be some sort of gradual change like that. Sorry, I just realized I'm probably not showing that. So it's not going to do something like this. Again, things that we associate with discontinuity. It's not going to do that, decrease, and then immediately be increasing. It would have to do something like this, all right, where it would slow down and then start to increase again. So again, we can assume differentiability, right? So it's saying that the derivative of that function, s in our case, is going to equal the average rate of change over that interval. All right, so instantaneous equals average, or the slope of the secant line is going to equal the slope of the tangent line. All right, so we need to figure out what this is, the average rate of change. All right, so before we do that, let's just say let t equal 0 be the time when the truck passes patrol car 1. I'm just going to call it PC1. All right, so that would mean this is t equals 0 right here. Okay, so then we have to think about what the time is here. So we know that it's 4 minutes later, but remember, we're talking about miles per hour, so it's not helpful to say this is 4 minutes. We need to convert that into hours, right? So we would say it is 4 minutes, but out of 60. And so we would end up with at that it would be 1/15 of an hour. So then the truck must pass patrol car number 2 when t equals 4/60 or 1/15 of an hour. Okay, so then let's work on, sorry, I'm getting a little cramped here. All right, so we need to find what f of 1/15, right? Again, so that means our interval is 0 to 1/15. Right, so we need to find f of 1/15 minus f of 0 over 1/15 minus 0. Right, now again you might say, oh sorry, this isn't f, this is s. You might say, but I don't know the position function. That's okay, because I know its position here, right? When t equals 0, it's just like it's just arrived at that spot. So we would say within that 5 miles, it's gone no time at all, all right? So here we're going to say the position at time 0 is 0, right? And then the position at 1/15 of an hour, it's gone the full 5 miles. So we'll say this is 5. And then I've got 1/15 minus 0. So I end up with 5 over 1/15, which says that is 75 miles per hour. Dang, he was moving. Okay, so what that says, again, mean value theorem says that if I have a continuous function on a closed interval, which is differentiable on the open interval, then there is some point, again, I'll go back up here, there is some point in there where the instantaneous rate of change, again, that's our speed, or our velocity, where its instantaneous rate of change is equal to the average rate of change over that interval. So we just found the average rate of change, which was 75 miles per hour. So it's saying at some point C in that interval from 0 to 1/15th, he had to have achieved a velocity of, or an average velocity. He had to have achieved that slope right there, or that rate of change. All right? And so at some point in the interval, the truck driver was going 75 miles per hour. Okay. Hopefully that's not too bad. All right, there's one more thing that we need to talk about, and that is this useful alternative to the mean value theorem. So it says if f is continuous on the closed interval ab and it's differentiable on the open interval ab, then there exists some number c in that open interval such that f of b equals f of a plus b minus a times f prime of c. You might look at this and think, whoa, where is that coming from? But again, remember what mean value theorem tells us. It says that if f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a number c in ab such that f prime of c is equal to f of b minus f of a over b minus a. All right, so that's what mean value theorem tells us. So we just need to figure out how we can get from here to here, or show that these two are equivalent. So first thing I'm going to do is I'm going to multiply both sides by b minus a. All right, because again, I don't want a fraction. I want to get rid of that. So these will cancel out. And I've got f of b minus f of a is equal to b minus a times f prime of c. All right, and then I'm just going to move f of a over to the other side. And so we end up with f of b is equal to f of a times b minus, or not times, plus b minus a times f prime of c. Okay, now you might be like, what is the point of that? Again, remember when we talked about the alternative form of the derivative, that we said that there were certain cases where it was really helpful to have that, specifically when we had absolute value functions. So we did the limit as x approaches c of f of x minus f of c over x minus c, and we used that specifically when we were going to have a hard time taking the derivative because it wasn't differentiable there. We're going to find the same thing is true, that we'll come up with situations where it's useful to use this. So as we come up to them, we will talk about them. Okay, thank you very much.